Thank you, Dr. Naveen. At the outset, I thank Amity University for giving me an opportunity to share some experience. So, before I get into the presentation, I pray Almighty to give strength and immunity to all of us amid this COVID pandemic. I wish all of you a safe stay and stay healthy. The topic of today's presentation is case studies, site investigation for offshore and online development and integrated approach. We normally advocate this integrated approach, meaning perform a geophysical investigation, identify the geohazards, and then develop the scope of geotechnical investigations and combine all the data together and use that for the assessment and design of foundations. So I'll go through some of those artifacts in the investigations, both geophysical, geohazards, and geotechnical, the offshore developments, both in shallow waters, and I'll give you some introduction to how it is done in the deep water, and lastly, some few case studies on both offshore as well as some onshore projects. These marine or offshore site investigation can be categorized based on the water depth, that is up to 15 meters, we term it as near shore, where the procedures, technologies, people, process, all of them follow the onshore practice. When the water depth exceeds beyond these depths, then these methodologies, what we normally adopt in the onshore and nearshore locations, is not applicable because you need different kinds of equipments, you need different kinds of tools, experience. So thus we define the shallow waters up to about 150 meters beyond 15 meters. And the deep water is between 15 to 1500 meters. Ultra deep water is between 1500 to 3000 meters. So we do have deep water locations in India, east coast itself. Now, currently, there are some projects happening around 1600 meters water depth, where ONGC is also contemplating to have the development in the ultra deep waters around 2500 meters, maybe in the next few years' time. Richard Handy has beautifully said that virtually every structure are supported by soil or rock. Those that aren't either fly, float, or fall overs. In this course of presentations, let me introduce some floating structures also that is normally adopted for oil and gas exploration in deep waters. So usually the phases of oil and gas exploration will be twofolds. One is the exploration stage, the other one is the production stage. In the exploration stage, normally they will use these jackup rigs, which is a ship by itself, okay, and has three legs. At a locations, these legs will be lowered down into the water and touch the seabed. Slowly, the entire ship, we call this as hull, the entire ship will be lifted out of water from hydrostatic conditions, buoyancy. All the dead loads will be now transferred through these legs. The legs will start penetrating into the seabed and it will stop where your ultimate bearing capacity exceeds your applied load. Then once the leg penetration has stopped, then this entire hull is raised to an operational height. We call it as an air gap, normally about 8 to 10 meters. Then the cantilever will come out, and with the drilling rig, then they will drill for the oil explorations. So once the wells have been drilled, you find out there's a good reservoir, the quality is very good. Then the production stage will happen. During the production stage, the fixed platforms will be installed for pumping out the oil or gas. These platforms will be constructed by fabricating a jacket structures. I can see here the length of this jacket structure will be equal to the water depth. It can be a four-legged, as you see here, maybe a tripod, maybe eight-leg, depends on the designs. And this jacket will be appended on the seabed, okay, and then the piles will be driven through this jacket can and below the seabed. As you can see here, the piles are going below the seabed until the design penetrations are reached. Once the piling is completed, the entire jacket is welded to the piles, so where even the load of the jacket is transferred to the piles. There is a top deck which will be fabricated in the yard. They'll bring it and then place it on the top of jacket and weld it. So now you are ready for the production. The production normally happens through these conductor slots. You can see here, okay, and then the drilling will happen and reach the reservoir. Once the drilling is completed, then they start pumping this into the processing unit and further through the pipelines to the shore. When the jacket structure are appended on the seabed before piling start, this has to withstand the self-weight of the structure. So this is by means of what we know call as mud mats. These are the temporary seafloor supports. And this can be designed as a simple shallow bearing capacity problem. Various shapes and sizes are commonly used. Now what you see is a rectangle. It can be a square, triangle, or a circular shallow foundation. So once the jacket is lifted and placed on the seabed, then there will be a piling through the jacket cans, driven those in some hammers. Okay, and then the jacket will be welded to the pile, the top deck will be lifted, will be placed on these piles, and finally it is ready for the production stage. Now, the jacket structure is installed, constructed. Now, the jackup rig will come for the second time. So, first it has come to the locations during exploration stage. Now is a time for the production. The platform is installed, and the jackup rig will come for the second time. So, in this time, the jackup rig will come close to the platforms. The cantilever will be on top of the jacket, and it will be drilling the wells through the conductor slots. When the drilling is completed, this will go away, and then there will be a production until the life of those reservoirs, maybe 15 years, 20 years, depends. So what is the geotechnical challenge here? The foundation assessment of the jackup rig in open locations in the exploration stage. You need to make the assessment, the leg penetration, the risks and hazards during those installation of these jackup rigs. Mudbanks is a shallow bearing capacity. This is a geotechnical problem. And design of the pile foundations, again, is a geotechnical problem. So three phases: the pre-installation phase for the hammer selection, the construction phase during driving monitoring, and the post-construction phase for the capacity evaluations. And the geotechnical engineering will also be for the design of pipelines. As the explorations goes deeper and deeper waters, you see the piling are also longer and longer. Okay, beyond about 100, 150 meters, those fixed structures, we call it as compliant towers. Okay, some of them have been built 400 meters, maybe the recent one is 609 meters. These are taller than any of the monumental structures in the land that we all of us are aware of. Now, as the explorations goes deeper into deeper waters, the fixed structures becomes extremely difficult. The capacity is very less in the market. It's very expensive. So it's normal to adopt floating structures like what you see here, the semi-submersible for the exploration stage, and these are the production platforms in the deep waters. This is the tension leg platforms, single point anchor reservoir platforms. Okay. But however, this floating structure also has to be anchored into the ground for them to be positions during the life of those structures. So thus, geotechnical assessment is very important, extremely important for design of these anchor systems. In deep water is a very complex field. You can see these floating structures will be anchored. Okay, and there will be several wellheads, the production lines, the injection lines, the flow lines. Okay, and this is in 1350 meters of water depth. So all these shallow structures requires a thorough understanding of the ground characteristics, the geohazards, etc. We'll just talk of these things in the next few slides. So these are the deep water single point anchor reservoir projects. I'll talk about this Mad Dog Spar project. This is in Gulf of Mexico. It's a beautiful case study. I'll present this at the end of this presentation. Now, those anchoring systems can be many types. A simple plump weight, or we call it as a deadman anchors. The pile can be driven, and these anchors can be hooked to the pile. It can be a simple drag anchors. And generally, in the deep water, the suction anchors is very, very popular and very widely used. So, what does this do? You have a closed end at the top, open end at the bottom. So you have a pump at the top. Okay, as you lower down into the seabeds, then the water will enter first. There will be some sulfate penetrations. Later on, pump will be operated to pump out some water from the inside to create a pressure difference between the inside and the outside. Then due to this pressure difference, the suction will be created. It will suck the soil inside, taking the advantage of the weight of the water above it. This will be driven below. So there will be different stages of suctions created. So suction assisted driving of these piles by making use of the advantage of the water depth above the pipe. Okay, and then the anchors will be hooked to these suction anchors, and this will act as an anchor. It's very, very popular and very widely used for deep water applications. And of course, there are many other patented technologies, similar functions. Now, the elements to manage and mitigate risk for offshore development. First of all, this integrated approach to site investigation, which itself is a challenge. Now, once you get the characteristics of the grounds, identify the geohazards and the ground model ready, then it becomes very simple for the designs. And so, this is the same case for any structures, either it is built in the ocean or built in the land. And then you develop the terrain models combining the engineering geology, geophysics, and geotechnics. This is the information you gather from the integrated investigations. Of course, you have to have quality assurance system in place and risk assessment and mitigation assessment to be carried out at project commencement and reassessed at each key stage to the life of the project. Open and clear communications between all the stakeholders, and more importantly, you have to deploy skilled, qualified, and experienced personnel. Otherwise, the project will not be successful. Be it engineers, geologists, geophysicists, drillers, and maybe even during the course of the constructions, you need to have good project managers, construction managers, etc., for the success of these kind of projects. So we advocated this integrated approach. It requires multidisciplinary geo teams. You need to have the geophysicist, you need to have the geologist, the geotechnical engineers, and the designers, as I said. Also during the construction, you need the project management and the construction professionals, very experienced people for the success of these projects. So let me go through the geophysical part, how the survey is carried out and why is carried out. Normally, the geophysical survey is carried out to determine the bathymetry, the nature of seabed, and the subbottom geology of the proposed site, and also to identify possible hazards. It is very important. Maybe it is a seabed obstructions, it is an existing pipeline, there could be some submarine cables. You don't want to go and damage these things. There may be some poke marks, buried channels, rock outcrops. These are the hazards that are going to impede the safe installation of the structures. We need to evaluate those hazards based on the geophysical data. This geophysics also will aid in evaluation of engineering characteristics of shallow soils, and of course the correlation of seismostratigraphy with the borehole for evaluation of soil over the foundation depth, essentially to understand the lateral continuity of the strata. So I'll explain to you in the case studies. And normally you perform a hydrographic survey, maybe the bathymetry using echo sounders. It can be a single beam echo sounder or a multi-beam echo sounder. This will give you the image of the seafloor, sorry, the water depth, so we can give the characteristics of the seafloor. Side scan sonar will give you the image of the seafloors. It can identify any buried objects, shipwrecks, and so on. And subbottom profile will give you the characteristics or the stratigraphy below the ground. So the bathymetry is normally conducted like this in a grid fashion, both the directions. Okay, it can be a single beam where the data acquisition is only on one point. If it is a multi-beam, you have a swath bathymetry where the coverage is for a wider area, normally more than about 10 meters you can have in one single data acquisition line. And you get this envelope of the seabed, seafloor conditions. It's all very uniform. So you can see a mound at its locations. This is the side scan sonar, it's a towfish. Okay, then you get the data acquisitions. This image can be able to reveal the shipwrecks. There could be some ripples, sand ripples. There could be some poke marks. There could be some craters, etc. So the side scan sonar will be able to identify these things. Then the subbottom profile is to get the stratigraphy below the ground. So this is normally done by various equipments, the finger and the chirper. These are the very high frequency, but the penetrations will be very shallow. Okay. Normally between 5 to 10 meters. Boomer, it has a low frequency which can penetrate to deeper depths, particularly in the homogeneous soils. And Sparker will penetrate to deeper depths, and this is a high energy subbottom profiler. So when you do a subbottom profiler, you can get the characteristics or the stratigraphy below the ground. As you can see the example of the chirper data, very nicely the seabed has been depicted. You can also see the first layer, this is an isopack, okay, the silt layer. Then you have a gravel deposit. You can have the rock heights. Some accumulated shallow gas can also be determined if it is at the shallow depths. As I said, the chirper and the finger data can only give the data, very good data in the top, about 5 to 8 meters. This will be very good for your pipeline engineering. You can use this data for your shallow foundations. And the boomer data penetrates little deeper. And you can see this is a channel features. Okay, interpretation of this can be seen like this. Okay, so this is a channel feature which was a river flowing several thousands of years before. But recently there is a formation happens and also the very young formation. So the blue line is a seabed. The immediate red line is a layer interface between a very soft place and this layer. Okay, this channel is a hazard. Nobody want to put their foundation, particularly jack-up rigs in a channels because this is a flank, is a predetermined failures and it leads to distress. And these layers will identify the strata below the ground. Now, these geophysical surveys normally carried out in shallow waters. As you go into the deeper waters, maybe 1,500 meters, 2,000 meters, those tools on the surface will not have the resolutions to pass through those water columns. So how to get the data in deep waters? Generally, all those equipments will be housed within these autonomous underwater vehicles, AUV. Okay, this will be remotely controlled. It will be launched from the vessel, and it will be taken almost to the bottom of the water column, that is about 3 meters off the seabed. Then you do the survey in a grid pattern, okay, and then you bring it back to the deck. This is very popular to use these autonomous underwater vehicles for the geophysical survey in deep water. The same bathymetry, multi-beam, uh, side scan sonar, and the sub-bottom profiler. Once you have carried out the geophysical survey, the next step is to identify the geohazards. These geohazards can be described as site and local conditions, that is the seabed features or near surface events, having a potential of developing into a failure event, causing loss of life or investments. Okay? So let us examine that. I said the channel feature itself is a geohazard. Just doing a borehole will not be able to get these informations. Okay. In the absence of geophysics, if you move the rig at these locations, those foundations will be in a flank, is a predetermined failure, and you could see the distress to those structures. Thus, the geophysics will be able to identify the geohazards and safely. If you find these channel features, the best thing is to avoid it. So move the locations maybe to the left or to the right, that is devoid of these channel features. So I'll explain to you in one of the case study. In deeper waters, if there is any seismic event on the continental shelf, there could be some submarine slope failure. This will lead to your mud flow into the abscissal plane. Okay. So what happens here, when the mud flow happens, the debris flow and the turbidity current, you see the shear strength. This will be drop from 50 kilopascal almost nothing. So it will be almost like a fluid. So what happens if your infrastructure exists already with an anchoring system? There is a submarine slide happening, and this will knock off these anchors. So that will jeopardize the safety of those infrastructure, right? Thus, it is imperative that these geohazards to be identified, then accordingly locate the locations which is safer for any of those infrastructure. So in the deep water, the east coast of India, I think Reliance has done a good project. Ravi Bastia worked for Reliance, was a Padma Shri awardee. He has presented this paper. It was published by Springer. Okay, and identified several geohazards in the deep water east coast of India. But out of all of them, most significant is the slope instability because the sedimentation from the rivers joining the oceans, and then any events trigger like seismic events, then the slope stability, because it's a continental shelf, is most vulnerable, and almost all the geohazards will be due to the slope instability. Of course, there are some canyons and other. Let us examine a couple of them. This is in the east coast. You see these black lines demarcating the basins. The top you have the Mahanadi basins, okay. Then you have the Krishna Godavari basins, and this is where the existing oil and gas is happening. And you have the Kaveri Palar basins. As you could see here, the gray ones has a very low slope. The red ones has a very steep slope. This is a continental shelf. Now, very few kilometers, the water depth drops from maybe some 100 meters to 1,000 meters within a short distance. And these red ones are very steep slopes. And the blue and yellow ones are the normal slopes. Deposition of these sediments from the rivers is a growing concern. And also the slope stability will pose a lot of geohazards. So one of them is the canyons. So these canyons can be identified by your sub-bottom profilers. These are the conduits for high sediment flow. Okay, so what happens when your structure is almost in line with this sediment flow? This will knock off. So we don't want to put any structures where there is a canyons. Okay, and in addition to these canyons, there could be some submarine channels. You see, there is a flow direction, a lot of channels. Okay. So we don't want any structures to be on the direction of these channel features. So if geohazards are identified based on geophysics, you can safely relocate this to some other place where these mud flows will not impede and jeopardize the safety of those infrastructure. Now, so when you have done the geophysical survey, you have identified the geohazards. Now the next step is to carry out the geotechnical investigation. So the knowledge of seabed, soils, and rock is essential if the offshore structure are to be built safely and economically. And the offshore site investigation involves special problem raising the question what is sufficient. So you need to have enough data to represent three-dimensionally, both vertically and laterally, all the stratigraphy as well as the ground models. So that is the strength and deformation properties of each of those layers and the geohazards based on the geophysics. So the success of these integrated site investigations depends on well-prepared budget. If you don't have budget, nothing will happen. You need to have good planning. For example, the geophysics should be done first, then the geohazards, okay, and then the geotechnical investigations. So sometimes we have seen that there will be a parallel activity. Geophysics and the geotechnicals go hand in hand. So what if you have located the boreholes and later on you identify the geohazards based on the geophysical data, and these locations is not feasible. So you may have to go and redo the boreholes again. So that's again comes with cost and time, etc. So that's you require a thorough planning of all the activities in this integrated site survey. Finally, attention to quality and safety to develop an acceptable risk profile. We need to deploy qualified and skilled people. I already explained to you at the beginning. Otherwise, the entire activity will not be successful. So the geotechnical investigations normally is carried out by a dedicated drill ship which has a moon pool that is opening at the center of the ship and also a dedicated drilling unit. Okay, in shallow waters up to 100 meters, these drill ships will be positioned at the locations using anchors. That is at the four corners, maybe around six anchors or eight anchors, depends on the size of the vessels. Okay. If the water depth exceeds these 100 meters, then anchoring systems will not work because paying out and pulling out the anchors itself will be very tedious. You need big winches and so on. It is very time consuming. And thus, for those deeper waters, more than 100 meters, the best way is to use the dynamic positioning systems. That is, the bow thrusters will be operating continuously and without anchors. This ship will be held in positions using the dynamic positioning system. For the seabed mode of sampling, you use DP1s. For the drilling in deep waters, where you do a soil borehole and collect samples, you need two dynamic positioning systems, which are one as the backup. So site characterization in offshore involves in situ testing and laboratory testings on the samples that is recovered from the investigation itself. So the in situ testing enterprise comprise of your cone penetration testing, your field vein test. This is conducted in situ in the boreholes, and T-bar penetrometer and the ball penetrometer. You can see the T-bar and ball essentially for very soft place because of its area. You normally use this T-bar and ball penetrometers. The procedures are similar to the cone penetration test. Instead of the cone, you attach this ball penetrometer and T-bar penetrometers. So during the sampling process, you see the stages involved. You need to drill the samples, collect the samples, use Shelby tubes with an area ratio of about 10% so that the disturbance will be very, very minimum. Process these samples, storage, transportation, extractions, prepare this for the testing in the laboratory. There are two modes of investigations, particularly the drilling mode and the non-drilling mode. In the non-drilling mode, you tend to push the in situ testing to get the data from the seabed until the depth that these equipments are capable of. Or you can also collect the samples at one shot from the seabed until the depth that those systems are capable of recovering. If the data seabed mode is good enough for your designs, then you can terminate your investigations. If it is not, then you have to resort to a conventional boring system. These are some of the in situ testing seabed frames. All of them will be lowered into the seabed. Then, if it is a cone penetration test, it will be pushed. If it is the samples, then you can push the samples itself. Generally, the seabed sampler will be three types. One is the gravity core, vibro core, and the piston core. Okay. In the gravity core, you have a cutting shoe and this is a core barrels. Normally in the gravity corer, we also call this a drop corer, the core barrels will be made up to about 3 meters and then you have a dead weight at the top. The entire unit will be lowered down into the seabed. It allowed to penetrate under sulfate and finally you recover it to the deck and you have samples about 3 meters. This vibro core, the core barrels can be made even longer, maybe up to 6 to 7 meters, and you put electric motor at the top to vibrate, essentially to penetrate cohesion-less soils. Okay. If you want little deeper depth of investigations, you want to have the longer, then use the piston cores. So piston cores are like this. You make up the core barrel little longer, and the maximum I have seen about 30 meters in one shot. You can make up these core barrels with a dead weight at the top, and you have the lever arm and a counterbalance. Okay. Now the entire unit will be lowered down into the seabed, where the counterbalance touches the seabed first. The lever arm will be lifted up. Okay, this gets unhooked and disengaged from the dead weight hook there. And once this happens, the entire barrels will be dropped into the seabed. It will penetrate and the soil samples will enter the core barrel. Okay. Now, once this has stopped the penetration, then entire unit can be brought to the deck. You can see the piston corer penetrating the soil. You can see the soil smear here. Once it's brought to the deck, then you can remove this cutting shoe. There will be a PVC liner inside. You can pull the PVC liner, cut into pieces, a meter of pieces, and you have the soil samples. Now, I have seen in project that we have made up the barrel up to 33 meters. We got samples up to 22 meters in one shot. So designing your anchor system, which is about 15-20 meters, the data is good enough. Maybe you can just get away with the further investigations. I draw your attention here. This is the ultra short beacon line. This will record the coordinates where you are collecting the samples. Otherwise, you don't know which locations you are collecting the samples. And you see, these are the liner samples inside. These are cut into 1 meter pieces. And you can subject this to normal routine testing. So we'll just talk about what are the tests to be performed. It's also practice to collect some grab samples to characterize the seabed samples. Okay. And this is a cone penetration test. The seabed mode, you push the cone, you make up the cone rods up to maybe around 30-40 meters and start pushing this, and it can penetrate maybe around 30 meters and you get the data from 0 to 30 meters without a borehole. That's what normally we also do in the land rigs. You know, we start pushing the cone from the ground until it penetrates or refuses, then you get the data to that depth. So if this top 30 meters is not good enough, for example, pile foundation, you need 100 meters depth of investigations, then you may have to resort further in the downhole mode. And also the pipeline, the top half a meter of the data is very, very critical in the offshore for developing the seabed friction, trenching systems, and also to evaluate pipe settlements. So generally, this is done by collecting the box samples. You see the cube, 0.5 meter cube box samples. You collect the samples and immediately you then do this T-bar penetrometer, CPTs, ball penetrometers, and collect some undisturbed samples here and subject that for further testing onshore. So this will give you a very good coverage of this top half a meter, particularly useful for pipeline engineering. Then the next step is the downhole mode. So where your seabed mode is not enough, you may have to resort to the downhole mode. Is normally done by the vessel dynamically positioning system. You lower the template, seabed template, which will provide you reaction, and you have the drilling rig at the top. You lower the drill pipes and you collect samples here from the mud line. You collect samples, okay, then wash through this, collect another sample, wash through this, collect another samples, and continue until the intended target penetration. So instead of samples, you can also perform the in situ CPT test or the vein test. You push the cones here, then wash this borehole until that depth, then further you push the cone, then wash the depth and continue until the intended penetrations. There are many survey vessels I could see here, which has a dedicated drilling rig, and you have a moon pool at the center. I had the opportunity at least to work on all of them as a quality control engineer representing the owners. These are all the shallow water vessels which will be anchored and then positioning at the locations for drilling. So these are the deep water vessels. This is a Russian vessel called Bavanit. And now these days there are few more assets that can do the investigations in deep water. So the first step in any investigations, particularly in the downhole mode, is to establish the seabed. So once the seabed templates are lowered down, you have lowered down the drill pipes. The first step is to lower your bottom sensor into the drill pipes. It will come and nicely rest in this landing ring, okay, which is just about 1 to 2 meters off the seabed. So once this bottom sensor rests on the landing ring, the entire drill pipe is pushed down, is lowered further, and you see here the switch touching the seabed. It gets closed. The circuit gets closed. You put a bulb here, the bulb will glow on the top, right? So this is very important. So once you establish that mud lines, you mark 0 on the pipe to some reference on the deck, and immediately collect your mudline samples. Maybe you push 1 meter from that level, you get the mudline 0 to 1 meters. Okay. And then you wash that 1 meter and collect the second samples and continue until your designed penetration. You see the samples collected at various intervals. Okay. And offshore, these samples keep coming. Turnaround time will be around every 15 minutes. The contractors and the drilling systems are very good. And for every samples, you need to process it, cut the samples, do a lot of testings, and then pack it for further testing onshore. I draw your attention also, one of the important aspects is to utilize the mud. Okay, the consistency of the mud should be of this order, the Marshall funnel between 60 to 90 seconds. So you take the mud with a known quantity and maybe a liter and pour it into this funnel closed at the bottom. And later you record the time to empty this drilling fluid. If it empties around 30 seconds, that means it is very highly fluid, so you add more mud. If it empties in 120 seconds, it's very, very thick, you won't add water. So you try to get these details and then accordingly have the consistency such that your Marshall funnel will be around 30 to 90 seconds. And also you can measure the viscosity within this scale. You fill up this cup with the mud. Okay, this is a graduated scale. Here you see the bubble. So you adjust it like a triple beam balance, and directly you can read on top of the scale what is the viscosity. 9 parts per gram is the general viscosity that is preferred for the drilling fluid. So what happens if you don't use appropriate consistency of the mud? Then the boreholes are not washed properly. You will end up having wash samples. So these are not the gravels, but actually clayey sand. Okay, all the fines have been washed, and then you see only these gravel pieces. So this is badly disturbed. We don't want to see that kind of material. And also, if the boreholes are not washed properly, even cohesive soils, it is very difficult to get the undisturbed sample. These stiff clays, now you have the soft consistency. So it is imperative that the boreholes are nicely washed and use appropriate consistency or the viscosity of the mud for keeping the boreholes clean and get good data. Sometimes you also tend to get very good undisturbed samples in sandy soils. So the experience is very important. Those engineers who are very inexperienced, they cut the samples and take pictures. Rather, you would have preferred to nicely pack the samples for further testing onshore. So that's where your training is important, your experience is important. You need to always deploy experienced manpower on the job. So these are very, very expensive activities. So what are the tests that is performed offshore? Torvane, minivane, pocket pentometer, and unconsolidated undrained. These are the undrained shear strength measurements. Then you have the unit weight, moisture content, reaction to HCF. So let us examine each one of them. So this is a torvane. You have the vane blades. Okay, you press it into the flat surface, and then with a uniform vertical pressure, you try to rotate this and allow the soil to shear. It cannot slip; it has to shear. Once the soil shears, then you can read on the graduated scale at the top directly the undrained shear strength. Okay. And this is a miniature vane. The vane blade is inserted into the soil. You have the springs of different stiffness. You have a zero reading, then rotate this such that there will be a shear of the sample by the vane blade, and you note down the final degree. You know the degree of rotations, and there is a calibration constant for the combination of the spring and the blade size, kPa per degree. If you know what is the degree of rotations, you apply that constant, then you can get directly the undrained shear strength. And these are pocket pentrometers. You have a stylus or a spindle at the bottoms. You call it a stylus, one diameter into the soil. You push it. You have this calibrated spring, the graduated scale. This will directly read your unconfined compressive strength. Half the unconfined compressive strength is the undrained shear strength of soils. The next step is your unconsolidated undrained triaxial test. This is very popular and more reliable because of the confining pressures. You're bringing these in situ stress conditions. Okay, and then you have the stress strain curve, develop the deviator stress. Half the deviator stress is your undrained shear stress. I'm sure these are all very basic testing that will be followed on every meter of soils. Water content, you can do it for every meters. Unit weight, you know the volumes, you take the weights, you get your unit weights. And very important reaction to HCl. 10% HCl, you just make drop one or two drops on the soil and observe the reactions. If it's no reaction, then it doesn't have any calcium carbonate content. If it is vigorously reacts, that means this soil has high calcium carbonate content. So when you see a vigorous reactions, then you subject these samples for further testing in the onshore laboratory for calcium carbonate. So higher the calcium carbonate, more problematic is the soil. For an example, if you have a sand, it is siliceous sand and a carbonate sand. So the carbonate sand, the capacity will be almost 1/5 of what a pile capacity in a siliceous sand. So it is very important to characterize for the carbonate content and appropriately develop your ground model for the design of those structures built in that kind of soils. Soil structure, you see these lichens, these are not the knife cut. Okay, these are the weak planes exist in the ground. Under low stress conditions, this failure will happen and the surface will be soapy structure. So we need to record, identify this as a soil structure in the logging part. And also you can see the samples coming out of sample tube is expansive. So this indicates there could be some accumulated shallow gas. When you see this kind of expansiveness, you better be careful because there could be blowouts. Right? This is a high pressured accumulation of shallow gas within the. And nicely you pack these samples further testing onshore. It has to be stored vertically and transported without disturbance. For deep water samples, one will store in a refrigerated containers to maintain at 4 degrees. This is a requirement so that temperature changes will drastically alter the properties of those samples, particularly the deep water samples. So friends, we have seen the geophysical survey in both shallow water and deep water. We have seen what are the geohazards and the geotechnical investigations both in the seabed mode as well as in the downhole modes, and what tests to be performed on those samples, and further use all the information for the design of foundations. So now I'll just go through some few case studies. The first case study will be shallow water mud mats. It's a simple bearing capacity problem, right? So you can see these mud mats can be of different shape, different sizes. Okay. And very important when the investigations is happening for the piled foundations, okay, when your interest is about 150, 30 meters, the top 5 meters is of no consequence or significance for the design of foundations. The contractor simply generates a 2 to 18 kilopascal of design profile the top 4 meters. Okay, so this is a design profile by the contractors, but closely examine all the other tests that is performed. Okay, you could see that the shear strength is only around 4 kilopascal in the top 4 meters. This may essentially not hamper your pile designs, right? What it does definitely your bearing capacity computations. Now you're overestimating the shear strength. That means you are not conservative. So you are under predicting the capacity. Over predicting the capacity. Okay. So, and also the seabed itself could be a mound, right? If you don't have the geophysical data, you will not be able to identify. So what if the 4-leg jacket, one of the corner of the legs is on this mound? The other three are leaning towards one side. Okay, and this is what you have can happen. The jacket structure, four-legged, appended immediately after unhooking from the crane, it capsized. So $40 million gone into the oceans. Maybe the geohazards have not been identified for this location. Probably, perhaps added to it, the shear strength at the top 4 or 5 meters was not interpreted properly, and thus there could be a bearing capacity failure. There could be also a geohazards due to the slope instability, seabed instability. This is a tripod jacket. Okay, this is a triangular mud mat. This was in Indonesia. The piling was completed. During the construction of the piling, the contractor took about 2 extra days to level the jacket before the piling happened. So they complained to the owners that geotechnical data supplied by the owner is inaccurate, and thus they have to spend 2 additional days in leveling the jackets before the piling started, and they claim for the variation amount. Then the principal client, they said that if you can get a certificate from Dr. Partha, then probably we'll look at your variation and try to reimburse. So principal client was also my client. I represented them supervising this geotechnical investigation. And the contractor was also my client. We involved in during the construction for monitoring the piles. If you closely examine, you see a soft layer on 3 kilopascals. Below that is very strong layers. Okay, and I already explained this, how important it is to establish the seabed and collect your mudline samples, and also use a liner samples in very soft place. No, otherwise it will slip there. So these are polycarbonate liner materials. All this process was followed there, and thus has to reject as these data were of highest standards. So the contractor could not claim further, but we went ahead to see what was the problem there, the locations. If you examine the bathymetry chart in these circled locations, you see the bathymetry is around 82.3 to 82.5 meters, as against the rest of the locations about 81.4 to 81.6 meters. This is a trough at these locations. Probably some part of the triangular mud mat was in this trough. So this was also evident from the multi-beam that this platform was installed in the seabed trough. We closely look at the data and zoomed it. You could see that one of the corner of the mat was placed on the slope. It's a very soft place, and this is very, very important, and people ignore these correlations between the geophysics and geotechnical data. This was not considered during the installation phase, and thus they have to put the jacket on the slope, which took more time. And thus we said that you have not considered the integrated approach, and finally client did not pay any money. Next case study is the jackup rig. You see the same tripod with the jackup rig coming for the second time during the production stage. Okay. Now, when you have a geophysical data, when you locate a boreholes within the channel features, this is a channel, the yellow one you can see, the orange one is the channel. You don't want to locate your borehole, jackup rig in the channel features. So with the availability of the geophysical data, you see that there is a channel features, then you tend to push it outside, right? When you push it outside, this is devoid of the first channel, but you still see a second channel, little deeper depth. We also do not want, because if the jackup rig penetrate this layer and come and stop here, this will be again in the flank. And thus, the third locations was identified, and this was devoid of both the channels in directions, northwest. And so with east direction, this location was devoid of both the channels. And this is very important in the planning. So why this happened? Because the geophysical data and the geotechnical survey was happening simultaneously or parallelly. That's why you don't have time to make an assessment of the geohazards, and thus they have to redo the boreholes in these locations. So that's why always you need to plan ahead on a phased manner. This is one deep projects. Actually, one of the projects for approval of my CV, people said that you don't have experience in working in deep waters. So I had to go and give them evidence to show that I have worked in this drill ship. This is a deep water drill ship was in Malaysia. We went to the site. Also picked up, okay, in 2005, this was a Russian vessel, Bhavanit. So later, I think probably they accepted to review the data, but then I'm not going to present this because of the confidentiality of the data, but I'm going to present, which is much more interesting, which is already been published. So this deep water for a floating production offloading facility is a Mad Dog spar development project in Gulf of Mexico in 1348 meters water depth. Okay. So you see these floating production systems will be in the anchors. You have the cluster 1, cluster 2, and cluster 3. As you can see in the image itself, these are the debris flow, mud flow. This already happened. So the stratigraphy here will be highly heterogeneous. Thus, you require to intensively investigate. Okay, you have one borehole, one CPT for each of those anchor locations. On the contrary, you could see these two locations are in fairly uniform site. Okay, and you see the number of boreholes. There is only one borehole and two CPT, and here there is only one borehole, one CPT. That means 50% of the scope of geotechnical investigations has been minimized based on the geophysical data. So let us examine this. So this is cluster 2, where you have one borehole, one CPT for all the anchors, and all the anchors were successfully installed. And this they have to perform because there is a debris flow and the materials is likely to be very heterogeneous. And this was what was figured out during the investigations. And the course analysis suggested that this debris flow deposits in the slump core. And these were highly variable since they were deposited as part of massive debris flow, and the soils in the debris flow deposit consist of interbedded zones of soft debris flow material, silts, sand layers, and stiff debris flow blocks. On the contrary, the clusters 1 and 3, these other two clusters were located where very uniform and continuous sediment layers existed. Okay. You see the subbottom profile between the cluster 1 and 3 is so homogeneously and laterally continuous. All the layers 1 to 7 is able to detect throughout the subbottom profile between the clusters. That is, it is laterally continuous, right? And thus, they said that there is no need for any additional data, and the geophysics helped them to minimize the scope of geotechnical investigations by almost about 50%. Okay. Now, you could also see that in the CPT trace that there are heterogeneous in the cluster 3, the 3 CPTs done in the other two locations are on top of each other, indicating is pretty uniform. So now I get into the last case study, maybe another 5 minutes, I'm going to conclude. This is for an onshore development. This project was in Yemen. Okay. They wanted to build storage tanks to get rid of the floating production facilities that was in the offshore. They plan to have 4 tanks at these locations. As usual, as part of any investigations, the phased approach was followed here. Preliminary survey comprising your geophysical survey and the geotechnical investigations, and the detailed survey, the geotechnical and the geophysicals. During the detailed survey, the geophysical methods was very low frequency electromagnetic method that was followed. So these are the data points. The blue ones scattered are the preliminary geophysical data points. Okay, and you see these are the geotechnical boreholes during the preliminary investigations. Finally, when they located these tanks, then the green ones are the detailed geophysicals, and those inside are the boreholes, detailed geotechnical boreholes. The conclusions drawn from those reports in the preliminary geophysical survey, no major cavity or fractures or joints are present in the study area. From the geotechnical survey, these cavities or voids do not seem to be widespread. So these are the conclusions drawn from the geotechnical preliminary survey. As you could see, the plot of the N values, N50, you see here, in the top 20 meters, N is less than 50. So this is a compressible zone. Okay. Beyond that is a refusal stratum. Limestones is an incompressible zone. So our interest will be the top 20 meters. In the detailed geotechnical survey, no cavities or open joints or cracks were observed in any of the drilled boreholes. That was the conclusions drawn. But in the detailed survey stage, the geophysical methods, very low frequency electromagnetic methods, identified the small cavities are around 5 to 6 meters below the ground in tank 1 and in tank 2. So this actually puzzled the people, okay, how these cavities will impede in the safety of the foundation. Actually, this is a very large diameter tank, about 85-meter diameter, and these small cavities would really not matter. The arching effect can close it. Okay, but they were all puzzled, and all of them, the stakeholders, decided together that they have to open up. Okay, before that, you see that the detailed geophysical survey concludes that two intermediate near surface highly fractured caverns were encountered between 5 to 6 meters. All the stakeholders wanted to open up and target those cavities, okay, and then backfill it back, and then you construct the foundation. They decided, okay, this is a tank for both 1 and 4. This is the target locations. This is the excavation area. When they started excavation, instead of this, they could see these high fractures and also fractures, but naturally filled with fine soils. Okay. So you see the large diameter tank area, and this is the excavation. And some of the fractures were as wide as around 300 millimeters to 400 millimeters. This really puzzled them again, and then they don't know how to go forward. That's how when they reached out to us, we reviewed the data and suggested them that we need to make this cavity assessment or cavity mapping by thorough investigations again on the grid fashion, both sides performing the electrical resistivity methods and all the four tanks. We suggested this to be around 300 meters on both directions. But they said no, they don't have budget because this is a non-tendered additional item. Since the tank diameter was around 85 meters, they preferred to have only about 125 meters. They said, okay, let us move on. Okay, the survey was carried out at 20 meters grids on both directions, about 125 meters. The survey period duration was about 6 weeks in Yemen. Surface tank elevation 1, you see this 1.9 meters, 2 meters, 8 meters, and 18 meters. Because top 20 meters was our interest, we did not see any cavities here except the small ones, so we cleared this tank to go ahead with the same foundations, whatever they were planned. And so with this surface elevation of 2, we did not see any problem. 2 meters, 8 meters, and 18 meters. We cleared this tank 2, and tank 3. You see this cavity interpreted, which was outside the influence of this tank. Therefore, we also cleared this third tank, and they continued to do the same foundations. Lastly, it's very interesting that this tank 4 interpreted huge cavities, okay, 5 meters, 8 meters, 13 and 18 meters. To have these cavities at all depths in the top 20 meters, about 30 to 35% of this test zone is infilled with cavities. Nobody want to put this tank when you see this kind of cavities, because even during hydro test there will be translational tilt. When this happens, there's no way to correct those tilt in the tank. The two options: one is to grout this, or to move this tank away from these locations. So the grouting to cater this volume will cost them around $5-6 million, they estimated. But sacrificing the existing foundations and move this tank away would cost them about $1 million. Then they were very keen that they will move the locations. Now they decided to move the center of the tank outside by about 25 meters. Now we have a problem here. So we do not have the data at these locations. Initially, we told them to have 300 meters, but they did only 125 meters. Now we have to do further survey here with some overlapping lines both directions and continue for these locations. Finally, lot of resistance. The client agreed that they have to do this survey, but apparently when they decided and the team was ready to go, Yemen unrest is happening for the last couple of years. This project is on hold. All the team has been demobilized. Probably when it stabilizes and recovers, there is no unrest. We may go back and do the survey again, and then we close these projects. Probably with this COVID, it may not be possible for maybe another 1 year or 1.5 years. I'm just waiting if this can conclude. So I sum up in few lines concluding my presentation. The shallow hazard geophysical survey plays a vital role in defining site conditions during an integrated geoscience study for both offshore and on-land developments. So I thank all the participants for patient hearing, and Amity University for giving me an opportunity to share some experience. I'll be very happy if there's any questions to address. Thank you very much.
Yeah, thank you, sir. It's a wonderful presentation and very informative. I have one question from our department because this offshore engineering only like NIT and IIT have these subjects, but for our students, if you want to learn this, what is the possibility from your end, sir? How you can support for our students, or like a UG, PG, and PhD students if they are interested, because it's a very important topic. I am aware of this offshore engineering, but if my students want to learn this, what is the support you can extend, sir, from your company?
We can have maybe some interns coming in because there are a lot of interns come who can join us. Okay, but we can conduct some small courses, short-term course to give a lot of informations on this offshore technical engineering. Okay,
Yes,
so we
sir.
can work out this. Maybe we can discuss and see how it work out for both of us.
Thank you. With this, I would like to complete my vote of thanks. I'm sure that our students, faculty, and staff members have benefited by attending this webinar. First of all, I wish to thank our director, Dr. S.N. Sridhara, for providing us with all possible logistic support towards organizing this event. And also, I sincerely thanks to our speaker, Dr. Parsarathi, for accepting our invitation to be a guest speaker for the webinar. And also, I thank Mr. Ankit Batra for his support for organizing this seminar. At the end, I once again heartily thanks to all participants, faculty, staff members, and students for their support and making this webinar successful. Thank you, one and all.